Um, Hi, everyone. I would like to begin today by acknowledging that we're meeting on the unceded lands of the Wurundjeri people of the Kulin Nation and express my respects to elders past and present. We're very honoured today to have a talk by Matt Jiwa, who has very recently returned from the United States. Matt is an alumnus of the Melbourne School of Psychological Sciences. He completed his PhD a few years ago, looking at some interesting work on information seeking, and then sort of extended that work and took it in some really interesting directions as part of his postdoc at Columbia University with Jacqueline Gottlieb. So I'm really looking forward to the talk. I hope you enjoy it, and take it away, Matt.
Right. Cool. Thank you very much for having me. So yeah, as Dan mentioned, in the last several years, I've been really taken with this idea of information demand, sometimes called information seeking or curiosity. Basically just how we decide which information to engage with and which information to avoid. One of the reasons I've been particularly interested in this is that in psychology, we often conduct a lot of studies where we'll give someone some information, and then we'll examine how they use that information to make some kind of decision, which is really skipping an important step, because in the real world, we don't just typically have information handed to us, we have to seek it out from our environments. And the ways in which we do this could be seen as contributing to a number of important modern phenomena. So things like the spread of misinformation and disinformation, political polarization, and conspiracy beliefs could all be seen as related to the way in which we select which information we want to consume. As a consequence of all this, there's a growing area of research that has really focused in on understanding the cognitive mechanisms that underlie this process of information demand. When it comes to examining this process in the constraints of a lab environment, one of the most popular approaches has been to use probabilistic lotteries. So something that might look like this. So here you have a 75% chance of winning $5, and you have a 25% chance of winning nothing. So for example, we might present a participant with this lottery and then ask them, well, how curious would you be to know the outcome of this lottery right now, rather than at some later point in the task? Now, typically in these tasks, knowing the outcome of the lottery doesn't confer any actual advantage. You can't use that information to inform your future decision-making or to obtain additional rewards. It's what we would call non-instrumental information. For now, we're really going to focus in on this type of quote-unquote useless information. As for why the lotteries themselves are a popular choice of stimulus, they're easy to quantify. They're flexible in terms of the stake that you could offer and the associated probability, and they can be used to examine behavior in both the gain and loss domains. So you can have lotteries that feature potential losses as well. What these studies that examine this behavior typically find is that in the same way that we refresh election maps on election night, or we check our exam results as soon as they're posted online, despite neither of those things having an influence on their actual outcomes, people tend to be very eager to know the outcomes of these lotteries as soon as possible. The extent of their curiosity typically depends on whether that lottery pertains to a gain or a loss, as well as to the probability of that gain or loss. So to get a sense of that variability, we'll first look at some past results. So this is one study that used probabilistic lotteries to examine non-instrumental information demand. On the x-axis here is the prior probability of winning some money in a binary lottery. So you can think of those pie charts from the last slide if that's helpful. And on the y-axis, you can interpret this as the strength of one's preference for information about that lottery outcome. So there are a couple of key features here that I want to highlight. Firstly, there's a peak in curiosity around lotteries with a probability of about 0.5, which makes some intuitive sense, because this is the point that we should be maximally uncertain about the lottery outcome. If it's a 50-50 chance, it's a toss-up, you really don't know what's going to happen. Whereas if it's 10-90 or 90-10, then you kind of already know what to expect. The second feature I want to highlight is that we find stronger preference for information about lotteries that have a high chance of winning compared to equivalent ones that have a low chance of winning. We'll explore why that might be the case later on. I just wanted to draw your attention to it for now. These patterns do replicate across studies. So this is a separate study with a similar design. Here they found the same peak in curiosity at these high uncertainty lotteries, as well as a stronger preference for information about prospective wins that are likely compared to those that are unlikely. This particular study also looked at lotteries that featured potential losses, so negative outcomes. And when they did that, they found a reversal of this latter effect. They found a higher interest in low probability losses than in high probability losses. Great. So the question then becomes, well, how can we account for these different behavioral patterns that we're observing? The most prominent account of this behavior in the literature is what I'll be calling the mixed motive model. Now, this model suggests that for non-instrumental information demand, we derive value from two different aspects of that information. So firstly, we derive what they called cognitive value from resolving uncertainty. What this means is that the more unsure you are of something, the more value you will place on information about that thing. For probabilistic lotteries like the one I've been describing, we can operationalize this in terms of, in this case, Shannon entropy. There are different measures of uncertainty. Some are more peaked or more flat. But what is consistent across all of those measures is that there will be maximal when the two outcomes are equally likely, so 50-50. Secondly, this framework suggests that we derive hedonic value from anticipating or experiencing positive outcomes. So the intuition here is that if you say probably won some money on a lottery like up here, you're probably quite interested in seeing that outcome materialize. Whereas if you probably lost some money down here, you might be much less interested in seeing that come to fruition. Again, for probabilistic lotteries, we can operationalize this in terms of the expected value of the lottery. So very high and positive for likely gains, low and negative for likely losses. Now, if we were to combine these two motives in a sort of linear regression weighted sum type fashion, we can start to produce behavior that matches some of those general trends that we've observed so far. So we do see a peak around these middle probabilities where uncertainty is high, but we also see greater interest in information about high probability wins compared to low probability wins, and about low probability losses compared to high probability losses. All right, so if we're able to leverage this model, there are some promising practical implications of this. By using this kind of simple lottery task, we could identify subject-wise differences in the extent to which someone's behavior is driven by, say, cognitive value or resolving uncertainty versus hedonic value, the emotional component of information. So for example, we might have participant A here do our lottery task and identify that they seem to be driven primarily by the hedonic value of information. They're very interested in seeing outcomes where they're likely to win and not very interested in seeing outcomes where they're likely to lose. In comparison, we might find that person B seems to be driven more by cognitive value. So they're interested in seeing information that resolves the most uncertainty, kind of irrespective of the expected valence of that information. And then finally, we could have person C who seems to be driven by both factors together. So we can see aspects of their behavior that seem to be consistent with maximizing cognitive value and aspects that seem to be consistent with hedonic value. What happens from there is, well, we can examine how these different behavioral profiles might be associated with or affected by a number of personal or situational factors. So things like age or developmental stage, trait and state anxiety, acute stress, emotional state, or agency or the ability to choose. We can even expand this to a neuroscientific analysis. So we could try to identify, for example, the distinct neural correlates associated with each of the two motives, so cognitive value versus hedonic value. All right, so that is promising in theory, but in practice, there are some shortcomings that I want to make note of. One is the fact that any differences in the subjective valuation of prospective gains versus prospective losses is automatically attributed to hedonic value. This is because hedonic value differs markedly for gains and losses, whereas cognitive value is seen as equivalent. Now, because hedonic value is positive for prospective gains and it's negative for prospective losses, what this means is that the model, as I've defined it up here, can never predict higher curiosity for a prospective gain, for a prospective loss compared to a prospective gain. So in practical terms, this red line here can never be higher than the yellow line. The two can never cross over. But as I showed earlier, this is not consistent with patterns that we do observe in the literature. So that is an issue for the model as I've defined it here. In addition to this, the neuroscientific findings that I alluded to earlier have been quite mixed, particularly with respect to the neural correlates of the hedonic value of information. So one study reported that activity in the mesolimbic reward system was valence dependent. It responded preferentially to information about potential gains, but not to the reveal of information about losses. However, in a different study with different authors, they found no neural correlates of the hedonic value of information, even at the whole brain level. And then in addition to this, a third study found that when uncertainty was first induced, there were a number of neural regions, that's this list here, that responded to the magnitude of that uncertainty, so the cognitive value of that information, but only one small region that responded to the expected value, the hedonic value of information. That was a small region in the calcarine sulcus, which is not typically associated with reward or decision-making. It's a visual area. Similarly, again, when that uncertainty was later resolved, they again found no neural correlates of the hedonic value of that information. So consistent with the null result from the previous slide. All right, so none of that is necessarily fatal for this mixed motive design, but at this stage, it might give us pause to consider some alternative explanations for the patterns that we're seeing. So where might we turn to find those? Well, since we've been dealing with probabilistic lotteries, a sensible starting point might be prospect theory. And in particular, there are two core tenets of prospect theory that I want to highlight as potentially very important. And I'll explain why after I introduce them. So firstly, we don't perceive probabilities linearly. This is a very well-established finding. It's a very core tenet of prospect theory. Instead, we tend to overweight small probabilities, so experience them as more likely than they actually are, and underweight large probabilities, so experience those as less likely than they are. The second factor that I think might be especially important is that this probability weighting might not be the same for prospective gains as it is for prospective losses. Now, there have been a number of studies that have attempted to examine how exactly our experience of losses and gains might be different. I'll show the results in the bottom right here, see if you can identify the common trend in their findings. So here's one study, here's a second, here's a third, and here's a fourth. So what you probably noticed was consistent across those results is that the subjective probability of losses was higher than the probability of gains. That loss curve was always above the gain curve. All right, so let's get back to what this means for information demand. The most important implication for me is that this implies that in our probabilistic lotteries, we should in fact experience uncertainty differently for losses as we do for gains. Now, if I was just to take these linear probabilities, so that gray dashed line going across the diagonal, and I put that through a measure of uncertainty like our Shannon entropy function, I get something that looks like this. It's symmetrical between 0 and 1, and it makes no distinction between gains and losses. But those are not the probabilities that we actually experience. So the question we should be asking is what happens when we take these subjective curves, the red line and the yellow line, and we put those through the same uncertainty function? Well, when we do that, now we get a measure of how subjectively uncertain we might expect someone to be when they're faced with a prospective gain or a prospective loss of these various different probabilities. What you'll notice here is that we have high subjective uncertainty about low probability losses, and we have high subjective uncertainty about high probability gains. Just to quickly get some intuition about why this is happening, if we look back at our probability weighting functions on the left here, if you look at the left-hand side of this plot, so when the probability is low, you see that because we overstate the probability of a loss, this loss curve ends up close to this point at which we're maximally subjectively uncertain at these low probabilities. Whereas on the right-hand side of the plot, over here, the underestimation of the subjective probability of a gain is making it so that we're more subjectively uncertain about these high probability gains. So that's why we're getting this pattern in this simulation over here. Now, if we were to compare this simulated data on the right to participants' stated curiosity ratings from that previous experiment that we just looked at, now it seems we're already approaching quite a close approximation of information demand for gains and for losses just by accounting for differences in how we experience probability. All right, so that's a lot of background, but that lays the theoretical groundwork next for how we constructed a task in order to conduct a formal comparison of this mixed motive account versus the new probabilistic reasoning account of non-instrumental information demand. So in our task, we had subjects play a series of lotteries, as you might expect. We framed these lotteries as fishing expeditions in ponds that look like this. So here the participant is told that they'll catch one item from the pond, either a fish that's worth $5 or a clump of seaweed, which is worth nothing. On each of these ponds, we asked the participant to rate how curious they would be to know the outcome of that lottery before the end of the task. We also had some trials where the fish were what we called toxic, and if you catch one of these fish, your bonus is instead reduced by $5. So these are the potential loss lotteries over here. They did a total of 80 rounds of this task, with each pond containing a different ratio of fish to seaweed. After they rated all 80 ponds, we selected and showed them one pond that they had rated at random, and the participant was told that whatever they had caught in this randomly selected pond would determine their bonus for the task. This is the only one that matters. They then completed a filler task, which was 15 minutes of surveys before the experiment ended, and they received their payment and kind of learned what they had caught in the randomly selected pond. In order to incentivize accurate curiosity ratings, we made it so that if the curiosity rating that they had given this randomly selected pond was sufficiently high, they might be shown which item they had caught before doing the filler task, so resolving their uncertainty ahead of time. Specifically, we made the likelihood proportional to their relative curiosity rating. I can explain the exact mechanics of how that worked at the end if anyone's particularly interested, but for now you can just assume that they were incentivized to respond as accurately as possible to this question. So we did fit our two different models to the collected data. Firstly, in the mixed motive model, as you might expect, curiosity ratings were determined by a weighted combination of the uncertainty or the cognitive value and the expected value or the hedonic value of the information. What you'll notice here is that for uncertainty, we're using a slightly different uncertainty function. This is the misclassification rate. We did try a few different measures of uncertainty, and this is the one that provided the best overall fit. Regardless of which uncertainty measure you use, the overall conclusions, the model comparison results are exactly the same. In the probabilistic reasoning model, we are calculating uncertainty in exactly the same way, but the probabilities that we enter into this uncertainty function, we first transformed using separate probability weighting functions for gains and for losses. Just briefly to describe this function here, this is the Prelec probability weighting function. It has two parameters. It has an alpha, which dictates the curvature of the function, so how steep that S shape is, and it has a beta, which dictates the elevation of the function, so how high or low the subjective probabilities are. As mentioned here, we fit separate functions for gains and losses, so each participant had an alpha and a beta for gain trials, and an alpha and a beta for loss trials. And of course, both of these models were fit hierarchically, so each of these parameters was at the subject level. All right, so looking at our results, we first found that, as we expected, curiosity did peak around these middle probabilities where uncertainty is highest, but was also slightly higher for low probability losses and for high probability gains. When we fit our two models, the mixed motive model failed to fully capture this pattern, whereas the probabilistic reasoning model did a noticeably better job. This was further reflected in model fit statistics that penalized model complexity, and in the model fit at an individual level, as it provided the best fit to the majority of participants. For one final check, we can extract the estimated probability weighting functions implied by our model fit. That's what I'm showing on the left here. And when we do that, we find that it aligns quite closely with the patterns we expect to observe in these probability weighting functions. So it has the S shape with an overestimation of small probabilities and an underestimation of large ones, as well as an overstated probability of losses relative to gains. So a nice sanity check, if nothing else. Okay, so far we've been looking at non-instrumental information demand. An important next step for us was to consider how each of these models could now account for the value of instrumental information, so information that can be used to improve your future decision-making and help you to obtain extra rewards. So just to remind you, in our first experiment, we showed participants a lottery. they potentially revealed the outcome early, and if not, they found out at the end of the task. Now, if we want to add an instrumental component to this task, we could add a step in the middle of this, where the participant is now required to guess which outcome has occurred. If we were to offer a financial incentive for responding correctly to this guess, then now all of a sudden, this early information revealing the outcome ahead of time now has instrumental value, because if you learn what outcome happens here, then you can use that information to inform your guess and make sure you get this extra $2 reward. In this situation, we can actually calculate explicitly the instrumental value of the information. So step one would be to assume that if you get this early information, you're definitely going to get the $2 reward. So the expected value of your guess, if you get that information, is $2. Of course, if you don't get that information, then your guess will just have to be a best guess based on the lottery that you have here. So here, your best guess is only 50% likely to be correct. So the expected value of your guess without information is $2 multiplied by 0.5. So that comes out to $1. What this means is that the instrumental value of revealing this information ahead of time is calculated as $2 minus $1. It's the expected value if you have information minus the expected value if you don't have information. So that comes out to $1. Yep.
So I think I might be missing something about both this task and the previous one. Was there a cost to saying that you wanted to know the answer? Because I don't understand why people wouldn't just say, I want to know the answer every single time.
Yeah. So for the previous experiment, the way we determined whether they were shown the information is we looked at the relative curiosity rating they gave the randomly selected trial against all their other responses. So we showed them a range of lotteries, and if you're really interested in knowing the outcome, if, say, a 50-50 lottery is shown, then you'll rate your curiosity high. And if you're shown a lottery that's 90-10, you'll rate your curiosity as low, because when it comes to revealing the outcome of the information, if that 50-50 lottery is selected to determine your outcome, then we'll compare your very high rating to your other lower ratings. In practice, we did this as like a Z-score and then reverse transformed that into a probability using the cumulative normal distribution. So that's how they were incentivized to respond: high curiosity for information that they were actually interested in, and low if it's not so interesting. For this one, it's slightly different, but I'll explain that in just a moment. Okay, so that's how we would calculate the instrumental value. We can do exactly the same for these various different lotteries that I've shown so far. So here you have a 75% chance of winning this lottery, which means that your best guess is now 75% likely to be correct, because your best guess is, yes, I'm going to win the $5. That means that the expected value of your guess without information is slightly higher, so the instrumental value is now only 50 cents. Okay, so that's how we would calculate instrumental value. Now for how we actually incorporate this into our two different models. So for the mixed motive model, it's fairly straightforward. It's kind of defined for us in this theory paper. We just add instrumental value as an additional motive. So here in the scenario I just described, the value of that early information would be the cognitive value you get from resolving uncertainty, plus the hedonic value of potentially seeing a positive outcome, plus the instrumental value of getting that guaranteed reward. For the probabilistic reasoning model, it's slightly different. We're instead assuming that the value of information in this situation is purely dependent on the instrumental value. But when we're calculating this instrumental value, as I described to you before, we're first going to take our probability, so there's 75% chance of winning, and we're going to look at how you subjectively experience that probability. So we can fit this probability weighting function as before. A second factor to consider is that we're now dealing with actual monetary values. We're not just dealing with these arbitrary senses of curiosity and uncertainty, which also means that we can take this monetary value and we can transform that using the value function taken from prospect theory. I won't go too deep into this, but just in brief, the value function allows us to calculate the subjective value, in this case of a monetary reward. It has two parameters, one that governs the extent to which increasing rewards deliver diminishing returns, and a second parameter that dictates the relative sensitivity to losses versus gains. Once we push each of these values through their respective functions, we can spit out a new equation that is exactly the same, but with these corrected values. So here we have an experience probability of closer to about 60%, which means that we are overestimating the instrumental value of the information. It's 72 cents compared to the objective value of 50 cents. Okay, so that is the theory of how we would calculate and model instrumental value. Now for how we actually went about measuring it so that we could compare our model fits. So we replicated experiment 1, but we made 2 key changes. Firstly, as you might have been able to intuit, we asked participants to guess which outcome occurred. So did you catch a fish or did you catch some seaweed on this randomly selected trial? They were informed that this guess would be made after the potential early reveal of information. So if they do get that information, they can use it to inform their guess and get the reward, which is, in this case, consistent at $2. The second change was that rather than a curiosity rating provided along an arbitrary scale, we asked participants to place a bid, which corresponded to the maximum monetary value they would pay in order to see this early information ahead of time before making their guess. This is a process that we used called a BDM auction. For those that are unfamiliar, I'll just briefly walk you through exactly how this works. So say, for example, you saw this pond, it's 50-50 chance of losing $5, and you decided the maximum amount I'm willing to pay in order to see which outcome happened before making my guess is 80 cents. That's where I'm going to position my slider here. So what does this actually mean? Well, when you make this bid, the computer will then generate a random price for the information between $0 and $2, so along the same continuum. If that randomly generated price happens to be below your bid, say at 50 cents here, that means you said, I'm willing to pay that. So I'm willing to pay anything up to 80 cents, which means you would pay the 50-cent price and the outcome would be revealed to you. So you would find out here that you caught some seaweed. Good news. If the computer's randomly generated price happens to be above your bid, say at $1.75, that means you've essentially stated, I'm not willing to pay that much for the information, so I won't. You'll pay nothing, and the information will be kept secret. Of course, then the trial continues. You then make your guess either with full information and get the $2 reward, or without information and make your best guess, which again, in this situation, is 50% likely to be correct. As before, we can calculate the actual instrumental value of this information by comparing the expected value with information versus without, and getting a final instrumental value of $1. This is important because the normative response on this BDM auction procedure is simply to bid the instrumental value of the information. So here your optimal bid would be to place your slider at exactly $1. Okay, so again, we fit our 2 separate models. Firstly, in the mixed motive model, we took our hedonic value from before, so the expected value of the overall lottery, and we added the instrumental value calculated as we've just been through. One thing to note here is that because the instrumental value in this lottery and the uncertainty measure from experiment 1 were perfectly correlated, we can't actually include cognitive value as a separate predictor in this model. Instead, we're assuming that this K instrumental parameter will actually capture the contributions both of instrumental value and of cognitive value or uncertainty. This isn't theoretically problematic, but what it does mean if we wanted to separate out the individual contributions of instrumental and cognitive value, we wouldn't be able to do so. Secondly, for our probabilistic reasoning model, we again calculated instrumental value exactly in the same way, but the reward and the probability that we entered into this function, we first transformed using our nonlinear weighting functions taken from prospect theory. All right, so turning to our results, we did find that participants adhered quite well to the normative behavior. That's the gray dotted line here. As I described to you, the normative behavior is to place your bid at the exact calculated instrumental value of the information. So for a 50-50 lottery, the normative response is to bid $1. We do see some notable deviations from the normative behavior. So there's an overbidding at low and high probabilities and an underbidding at middle probabilities. which is a pattern the mixed motive model was not able to capture, but the probabilistic reasoning model was more successful. Again, this was backed up by model fit statistics, both at the group level and at the individual level as well. All right, so at this point, I want to take a moment to acknowledge a concern that you might raise, which is it not just possible that these probability weighting curves and the value function you're using are just really flexible functions, and they're doing a good job of fitting this information demand behavior just because of that flexibility? Could this be the case without there being any true underlying connection to nonlinear probability weighting, say? And this is something we were concerned about too. So for experiment 3, we set out to address this. We conducted a task where a new set of participants completed 2 tasks. So they did the information seeking task, the instrumental task I just described, and they did a risky choice task that I'll talk you through in just a moment. The goal here was to fit probabilistic reasoning models to both of these sets of results independently, and then to compare the estimated functions to identify whether there were participant-level correlations between the parameters of these functions that they were using to do each task. In simple terms, what we were hoping to find out was, are participants using the same or similar probability weighting functions and value functions to do these 2 separate tasks? And if that's the case, then presumably it's not just the flexibility of these functions that is lending itself to producing a good model fit. All right, so before we get into the results, I'll first take you through what this risky choice task looked like. So on each trial, we presented participants with a field containing 10 mushrooms. These ones are either golden and worth $5, or they're plain and worth $0. So this should be kind of familiar at this point. This is just another lottery task where they're told they'll get a random item from the field, and whatever they get will determine their final reward. The difference with this task was that either they'll complete this lottery and get either the $0 or $5 reward, or they will get some guaranteed value that is between $0 and $5, as reflected by the box up the top right. Their task on each trial was to set a threshold between $0 and $5 that corresponded to the minimum guaranteed value that they would accept in exchange for foregoing their participation in the lottery. That's a lot of words, so let's take you through an example. Let's say you saw this field here with 5 golden and 5 plain mushrooms, and you said, I'm going to set my threshold at exactly $1.17. What does this actually mean? Well, this means that when the computer generates a random guaranteed value between $0 and $5, if that random guaranteed value is anywhere above your threshold, say at $4.23, that means you have said, I'm willing to accept that. I'll take that $4.23 and I'll sacrifice my participation in this lottery. If the computer's generated value happens to be anywhere below your threshold, say at 98 cents here, that means you're saying that's not enough money. I'm going to reject that value, and instead I'm going to get a random mushroom from the field. I will play the lottery. This is a fairly standard form of a certainty equivalence task. Just to briefly describe the normative behavior, here the normative behavior is to place your threshold exactly at the expected value of the lottery. So here the expected value of this lottery is $2.50 because you have a 50% chance of getting $5. So if you place your threshold at that expected value, then any guaranteed value that is above that, you will accept. Any guaranteed value that is below that, you will reject. We also had participants complete trials that featured potential losses. So here these poisonous mushrooms were worth -$5. Participants on these trials were setting their threshold between -5 and 0. And if the guaranteed value that the computer generated was higher, so less negative, then they would get that guaranteed value. So for example, on this trial, if the computer happened to generate a guaranteed value of -20 cents, you would be saying, I'll take that -20 cents and I'll avoid participating in this lottery. Again, they did 80 trials of this task in 4 interleaved blocks, and we fit a probabilistic reasoning model to the data using exactly the same probability weighting function and value function that were used to model the information demand task. All right, So looking at the results, firstly, of the information demand task, again, our participants aligned quite closely with the normative behavior of the normative pattern of information demand. We do see similar deviations, so overbidding over here and underbidding at middle probabilities, albeit to a slightly lesser degree than we did in experiment 2. Turning to the risky choice task, here the x-axis indicates the proportion of those golden or poisonous mushrooms in the field, and the y-axis is the average position of the participant's threshold. Again, I've plotted the normative response as these gray dotted lines going across on the diagonals. As I described, if you have a 50% chance of getting a $5 reward, the normative response is to place your threshold at $2.50. Similar to the information-seeking task, we do see that participants adhered relatively closely to this normative behavior, though there were some notable deviations that you can see, especially at low probabilities down here and at high probabilities up the end of the lines. You can kind of intuit how these could relate to the probability weighting functions, so the overestimation of small probabilities and the underestimation of large ones. All right. So the next step for us was to extract the probability weighting functions and the value functions that determined participants' responses in each task. Again, the outcome of interest for us was the correlation between the parameters of these functions at an individual subject level. Firstly, at a group level, we have the probability weighting functions here, plotted separately for the information demand and the risky choice task. It's a little bit tricky to see the two distinct lines because they are quite similar, but the two functions were slightly flatter than we typically expect to see. I can explore why that might have been the case at the end if anyone's interested, but we do still see the characteristic S shape, so the overestimation of small probabilities and the underestimation of large ones, as well as the slight overestimation of the subjective probability of losses relative to gains. To remind you, each function here is determined by two parameters, the alpha, which dictates the curvature of the function, and the beta, which dictates the elevation of the function. And when we extract those parameters at an individual level and plot them with the risky choice parameter on the y-axis and the information demand task on the x-axis, we did find significant positive correlations between each of these parameters across our participants. So again, what this suggests to us is that the conclusion I proposed earlier, that the probabilistic reasoning model is only explaining information demand because it's a very flexible function, that doesn't seem to be an accurate conclusion. Instead, this suggests that there may indeed be a shared underlying mechanism of nonlinear probability weighting. We did exactly the same thing for the value functions. Again, on aggregate, these were a lot flatter than we typically see, though there was a reasonable amount of intersubject variability. We extracted our two parameters, so we have gamma to dictate the diminishing returns, and we have lambda for the loss aversion. And when we compared these between the two tasks, we do find a significant positive correlation across our subjects. All right, so how do we then put all of this together? Firstly, the main conclusion is that when it comes to explaining information demand, both instrumental and non-instrumental information pertaining to these probabilistic outcomes, it seems that these behavioral patterns that we observe seem to be better explained by probabilistic reasoning than they were by a mixed motive account. This is an interesting finding that provides a potential bridge between the field of information demand and the broader, more well-established literature surrounding decision-making under risk. It is a potential two-way connection in which findings from one field could inform research questions from the other and vice versa. There are some caveats that I think are worth noting, though. One of which is that despite it not providing the best account of the behavior in our experiments here today, I do still believe there is a lot of value in this mixed motive framework of information, including in the hedonic value of information. What our results showed is that hedonic value seems to have little to no impact on information demand in the context of these low-stakes probabilistic lotteries. But despite this, it might still play a key role when it comes to information that pertains to more emotive matters. So things like medical diagnoses or issues that are really central to your personal or partisan identity. The types of things that would be especially relevant for these societal issues that I raised at the start of the talk. If that is the case, though, this means that our standard simplified information demand paradigms might not actually give us the window into the mechanisms that underlie these behaviors that we might have once hoped. And instead that we might need a different approach in order to properly understand these behaviors. That's everything from me. I firstly want to thank my supervisor, Jackie Gottlieb, for her fantastic support on this project. I want to thank Columbia and the Zuckerman Institute for funding it. As Dan did mention, I recently returned from the US on a permanent basis, so I am on the lookout for research opportunities. So if you know anyone who might be interested in working together, I'd love to chat. That's everything from me, so thanks for listening.
I think we've got about 15 minutes for questions. If you want to answer
Any questions? Yes.
That was a rich one. One of my questions, and I don't mean this in like a slightly facetious way, but when I was listening to the talk, I was trying to think about it. What would an annoying reviewer say about this? Because I remember reading Outperforms paper and thinking this doesn't sound like it's it. And one way that you could also model this would be, instead of having like linear weighting, it would be like some sort of non-linear way where one function kind of feeds into the other. So for example, hedonic value selectively weights cognitive value. I was trying to think about, does that kind of not really apply here, I guess, because nothing really has hedonic value, or could you say that kind of information is inherently kind of hedonic in that way to some people? So if they really value information, it might be something that you could say is highly hedonic.
Yeah, I mean, look, you could argue there is hedonic value to any of this stuff. I mean, I don't debate that, even a small win on a lottery, if you're playing it online to get some money from doing research online, that could be rewarding, right? The issue I have with adding these different caveats onto the mixed motive account is that it just becomes increasingly kind of post hoc, and we're now just trying to fiddle around to make things work rather than having this kind of simple approach that seems to explain the same findings without having to really dig our head into it. It just, based on what we already understand about probability and reward, we can kind of explain these things. That's my kind of short approach to, my response to that.
Okay, so then would you say that if there was some, like if you did have an experiment where you manipulated that, how would you model that? You just model it as in like the change in the function as a result of like hedonic value, or would you have hedonic value be into the function?
If you were to have a situation where hedonic value is relevant, that's a very good question, because I don't know that if you had a lottery that had a really big impact, right? So you say it's about $1,000, not about $5. I don't know that the expected value of the lottery is necessarily even the place to start for hedonic value, because that has no limit. You can just say, even if it's a 99% chance of winning, I still really want to see it because it has high hedonic value. That doesn't really just intuitively ring true. So I would be curious about how you could transform that hedonic value. Maybe, as you suggested, there's an interplay with cognitive value.
So I don't think this is semantically. First of all, this is really, really nice and elegant work.
Okay.
And I'm trying to imagine I'm one of the hedonic value people. And I mean, the thing that sort of jumped out at me is this whole thing in prospect theory. Why are gains and losses asymmetric? Maybe that's because we have different hedonic value gains and losses. And what you've shown nicely is that the particular functional form that they assume doesn't really capture the data as well. But if you're trying to sort of say, no, hedonic value is a thing, it comes into, would you just say it's the thing in terms of it affects your parameters of the prospect curve and the difference there. And so I guess my question is, does this make sense, and is that a possible answer to your question
Yeah.
about sort of how you might bring in hedonic value?
Yeah, that would make perfect sense. And in fact, particularly with the value function, right? You could have someone who has a very steep aversion to anything to do with losses, and that would make them much more sensitive compared to gains. That would, yeah, intuitively integrate hedonic value without it being this kind of post hoc. Let's just add something in. Yeah, I like that. Yeah.
Maybe I think you're maybe hinting at this toward the end of the talk. Have you thought about much about like how to take this theory and apply this like outside the line of the more probabilistic context predictions that test these models, or is that?
It would be an interesting next step. Not something that I've gotten to just yet, but it would be interesting to see whether we can still see these effects of probability in situations that aren't super on the nose with this is the probability, that kind of thing. As for how to go about that, I would really have to think about that a bit.
Yeah, I guess I was just thinking in terms of the broader kind of how much can we generalize from these particular paradigms? Question.
Yeah, I think that's an important question that I haven't fully gotten my head around. It's either that it's very constrained and only relevant to a specific setting, in which case we need a different approach if we want to understand these really broad societal factors, or it's that we need to find some way to translate this. And yeah, I'm not sure which of the two is more accurate at this point. Yep.
Thanks for the book. Really, really lovely, theoretically substantive stuff. I really like it. I'm curious to ask a question, just sort of pushing this framework a little bit further. Either predictions of the model that you have or kind of intuitions you have that could be built into a model. So one feature of the instrumental information seeking task you had was that you always received the information if you did well, the information that you received would always perfectly resolve uncertainty.
Yeah,
So
yeah.
I go from being 50-50 to 100% chance of.
Yeah.
My intuition is that perfect information is sort of a special case. People might treat perfect information as a special case.
Yeah.
Going from uncertainty to certainty.
Yeah.
Is qualitatively distinct, I think, than going from 50% uncertainty to 60%. 50% certainty to 60% certainty. Okay. Perhaps. I was wondering, the model that you presented, I think, would be constrained to treat that as, an increment in expected value of different size.
Yeah.
I was wondering, I just wanted to ask, have you thought about, first of all, what kind of data you might expect if you had more sort of intermediate degrees of information? Are there extra things that you would need to put into the model?
Yeah, it would be definitely interesting to test. It would be yeah. So firstly, with the full information being possibly a special case, that could be true, but it could also just be that even in the probability weighting function, if you're slightly unsure, that's still very different to being completely sure, right? Because of that real uptick at the end of the function. So in that case, that function kind of does some of the work for us. In theory, we could just apply this model without any tweaks. And as you say, we could go from your 50% on your probability weighting function to 60%. How much does that subjectively feel like? And because it's flatter than linear, we would say you're probably going to not be as interested in that kind of information as you probably should be. But yeah, really interesting, because in the real world, we don't often have this really deterministic information all the time, right? Things are quite incremental. So I think that's an important case for us to test.
Can I ask another question?
Yeah.
One other feature of this task, and also the modification you just described, is that you know what the change in probabilities are likely to be.
Yes.
That doesn't describe information seeking in the real world, where I may choose to seek out information and end up more uncertain than I was before.
Yes.
Or I may resolve my uncertainty. Do you think the sort of the tenets of prospect theory apply to information seeking as well? Do you think people are risk averse over updates to their belief?
It's a good question. Something that we could definitely definitely think about testing, because that would work in practice. As far as I can think about, the model could test that without any major modifications. So I don't know the answer.
What do you think with that?
Yeah, I think maybe people would be slightly risk averse to going backwards and saying, now I'm more uncertain, because we know that people really don't like uncertainty, and going backwards in the same sense of being loss averse to a loss of financial reward, that would make intuitive sense to me. So that's my intuition. Yeah, up the back.
This, I'm not familiar with exactly how much of a problem this can be in this kind of space, but do you think that some of the reason that people might just be like responding weirdly, well, not weirdly, but like not as optimally to probabilities they're presented with, is to do with how well they can actually translate what they see into a probability in their head? And if there is potentially an issue with people actually mapping that, does that affect the fact that you've also got one sort of not a linear scale, you've got like a display, and then you've got a linear scale, and people are kind of having to try and map between those two things? If they were trying to behave perfectly optimally, like maybe part of the reason people struggle near the end of that scale is just because it's actually quite hard to choose the right value in your head quickly.
Yeah. It's a tricky question, and I would be more concerned about that if the finding was not as well replicated as it is to do with the subjective probabilities and probability weighting. As for why that happens, as you kind of got to, I don't know if that's necessarily been particularly well answered. Yeah, one potential concern we had with respect to the linear scale and translating the display to the scale was, are we just seeing people overbid at some probabilities, at the outsized probabilities, and underbid at the large probabilities because they're just squishing all their responses in, they're not using the full scale? And one of the factors that we use to kind of persuade ourselves that this is not the case is that in the instrumental information task, the optimal response at the most extreme scenario was the midpoint of the scale. It's to bid $1. So they're only using that section of the scale, which would, if you were to constrain things in towards everyone's just responding closer to the middle, that would have a different effect than what we saw. So yeah, I don't know if that quite answers your question as yeah, but yeah.
Thanks so much for the talk. I think this is a little bit to what Dan was talking about, and this is far beyond the scope of what we've presented so far, but just the thought that I had. And I was wondering to what extent you considered or thought about like learning in these paradigms, and specifically I'm thinking about how, you know, when you're doing information seeking in the world, you know, maybe these kinds of like predictions, or like, yeah, you know, will this generate a certain outcome,
Yeah,
a gain or a loss or whatever.
Mhm.
You're usually learning like from people or from a source,
Mhm.
and so, you know, across time you can kind of learn the extent to which a source is like good or bad.
Yeah.
And I also think that, you know, some research shows that people are kind of resistant to outcomes if they sort of like have an initial perception of like a source being good or bad. And so
yeah,
again, beyond the scope of this specific project, but I was curious as to what your thoughts about how kind of like learning and having maybe, you know, a social element in information seeking, where you have somebody who's actually like providing this outcome, and yeah, how that relates to this as well.
Yeah. I think it's a really interesting question, because it's really getting to how you make this, how you go from these kind of abstract lotteries into something that you can really start to apply. And the way you've put that, it makes me think about how we could potentially model those kinds of dynamics. So for example, if you have a high trust in a source, or you really like a source, maybe you place more weight on the information that they provide and so on, and that you adjust your posterior probabilities accordingly, right? Yeah, I think what you've described also in terms of the learning effects would be, as you mentioned with respect to Dan's suggestion, that would be a really cool thing to incorporate into if you were to do these incremental rewards, or sorry, incremental changes in your perceived probability. How would that be affected by the learning, or whether you're just told explicitly this is going from 50% to 60% and so on? Yeah, really interesting questions. I don't have good answers to what that would look like, but hopefully one day.